All right, class. In this video, I'm going to be discussing what happens when we pull the two parallel plates of a capacitor apart when it's in a battery and when it is no longer connected to a battery. So for the first one, we have a capacitor of plate area A. So here, let me draw my capacitor here. So we got, whoopsies. Let's draw this a little bit cleaner here. Okay. All right, so we have our two plates. I know they don't look the same. That's because I'm bad at drawing. It's got a separation of D. It is hooked up to a battery of voltage delta V. Cool. So the first thing that we want to know is what is the magnitude of the charge on each plate? All right, so if that's the case, then the magnitude of the charge is just going to be Q. Right. If it's got an area and a D, right? We're not really changing anything around. We just want to start off with identifying that the charge is just going to be the total charge Q. All right. Next, what is the magnitude of the electric field between the plates? Well, if we're looking for the magnitude of the electric field, we know that delta V is going to be ED here. Or we can see, sorry, actually, let's go back to A. So if we want to find the magnitude of the electric or the charge, right? Q is going to be equal to C delta V, right? It's just the capacitance of the plates. Or we could go a little bit farther and we could say that, well, it is going to be delta V epsilon naught A over D, right? Since epsilon naught A over D is the equation for capacitance here, and then we just multiply by the voltage, and that should give us the charge. Now for the electric field, we have the change in voltage is equal to the electric field times the distance. So we can rearrange that. So we get delta V over D. Sweet. So this is for part B, and that is for A. All right. Now, what is the magnitude of the charge density on each plate? So if we want the charge density, well, if I want the charge density, that's the symbol. That's going to be the symbol sigma. So sigma is equal to the total charge divided by the area. Sweet. All right. So now we're going to leave the battery connected, but we are going to double the distance here. All right, we'll erase that. So now I'm not going to redraw it just for expediency, but now the distance between them is going to be 2D. So what happens when we double the distance? So first off, we want to ask ourselves, does this change the charge on the capacitor? Actually, I am going to go to a new page. All right, so now we have our new circuit. It is double the distance. And if we go back to our equation for Q, we find that the equation was delta V epsilon naught A over distance. In this case, right, it's 2D. So that means that we are dividing by 2. So that means our total Q is actually half of what it was, which makes sense because we've halved the capacitance, right? The capacitance is now, the initial capacitance is half as large, but the voltage is still the same, right? Which means that the Q is going to be half as large as it was before. So this is our answer for A. So how does this affect the magnitude of the electric field between the plates? Well, we have the same voltage across, right? So the electric field we wrote down as being the delta V over D, right? But in this case, it's delta V over 2D. So we are going to actually have half of the electric field, which makes sense, right? Because the voltage, if the battery wasn't connected, right, we would be keeping the same charge, and we'll get to this in a moment. But since the battery is still connected, there is not going to be as much pull for those charges. There's going to be half of the amount of charge. And we have doubled the distance, which we know voltage to be electric field times distance. So we need it to actually balance out. So for it to balance out, the electric field has to be half as large because the distance is twice as big. So this is our answer for B. Or sorry, actually these are not B's and A's. This is actually our answer for E. And this is our answer for F. All right. So next, how does this affect the charge density on each plate? Well, we've halved the charge. So that means that we're going to have the charge density, right? If charge density is Q over A, well, we've halved the charge. So that means that the total charge is going to be that, right? Q over 2A. Sweet. This is our answer for F. Whoopsies. I did that again. This is not F. This is going to be D. Sweet. All right. And then lastly, for when the battery is charged, how does this affect the energy stored in the capacitor? Well, when we look at the equation for, sorry, muted myself there. When we look at energy stored in a capacitor, we initially get the equation Q squared over 2C. But we can rework this so that it's going to be 1/2 Q times delta V, which is a little bit simpler because the change in voltage stays the same. Because it is one capacitor, it's got to drop the entire voltage across that capacitor. So the only thing that's changed here is the amount of charge, and we have half the amount of charge, which means that the total amount of energy stored here is also going to be half. Notice that all of these answers have been half the amount, right? The voltage is the same, but the charge is half, so the total energy stored is also going to be half. All right. Next, what happens when we when we do the same thing, but when we separate them, we have disconnected the battery beforehand. All right, so here is our capacitor. Notice it's no longer connected to the battery. So what we did is we brought them back together, we disconnected the battery, and then we brought them apart to that distance 2D. So first off, we want to figure out what's happened to the charge on the capacitor. Well, since it is no longer in the circuit, the charge can't flow, which means that the charge is still going to be Q, right? It's not going to be half as much as it was. All the charge on the capacitor is still the same. But what happens to the potential difference? Well, because the charge has stayed the same, we have, because the charge has stayed the same, but we've moved the two parallel plates apart, we've actually halved the capacitance, and therefore we have halved the voltage, right? So if C is equal to Q over delta V, which is equal to epsilon naught A over D, well, now it's actually going to be 2D. And since charge is going to be the same, we've actually halved the capacitance because we've done that, which means that we're going to have only, actually, we have increased the delta V, right? It's got to be half. The charge hasn't gotten smaller, but the change in voltage has actually gotten bigger, which makes sense because delta V is equal to ED, and we have doubled the distance, which means that we have doubled the change in voltage. Which leads us right into the next part, which is what's happened to the electric field between the plates. Well, because we've increased the distance, we've increased the change in electric potential, but the charge is still the same, which means that the electric field also stays the same. Stays the same. Stays the same. And I can write that up here too. Stays the same. Sweet. And then lastly, for I, what has happened to the energy stored in the capacitor? Well, let's go back to that same equation that we were working with before. 1/2 Q delta V. Well, the delta V has gotten twice as large, which means that our energy is also going to be twice as large, which makes sense, right? The charge has stayed the same on the capacitor, but we've increased the distance apart, which means that we have increased the potential energy. Just like when you lift something higher up in the air on Earth, right? If you double the distance from the Earth's surface, you have doubled its potential energy. So that is what happens when we pull two parallel plates apart.